Good evening and welcome to the 32nd Annual Faculty Lecture. I am Dan Luchtol, Professor of Environmental and Occupational Health Sciences and Chair of the Faculty Senate. Each year since 1976, members of the faculty have chosen someone who has made a significant impact on their profession to deliver the annual faculty lecture. This is the highest honor the University of Washington faculty can bestow on one of their own. Tonight's speaker, Professor Gerald Pollack, joins a distinguished roster of historians, artists, scientists, authors, and Nobel laureates who have participated in this series. Professor Pollack is one of the world's original thinkers on the structure of water, a liquid we see, drink, and largely take for granted every day. His research challenges some of our most basic assumptions about how water behaves and is relevant to diverse audiences. The repercussions stretch into every area of inquiry, from environmental science to cell biology to medicine. Advancing a bold theory is not a job for the timid. Jerry is up to the task. His scientific viewpoint questions long-held theories. In 2001, he summarized his work in the book, Cells, Gels, and the Engines of Life. In 2005, he wrote an article entitled Revitalizing Science in a Risk-Averse Culture. He advises the National Science Foundation on how to support cutting-edge research. On top of this, his enthusiasm for his work is truly infectious. He is author of 2 award-winning books for the general public and is an invited speaker at conferences around the world. Professor Pollack earned his PhD in 1968 from the University of Pennsylvania and has been at the University of Washington since then. He is a fellow of the Biomedical Engineering Society and the American Heart Association and is on the editorial board of numerous scientific journals. It is my pleasure and honor to present Professor Pollack, who will share with us his evolutionary theory of water.
Well, thanks, Dan, for that beautiful introduction, and I'm truly humbled by this great honor, and welcome this evening. I do want to talk about water, energy, and biology, and fresh views from the water's edge. Well, the water's edge has lots of fresh and beautiful views, and if you wander out into the middle of the water, as some of us may do, and you look up, you see sights that are very familiar, and yet maybe somewhat intriguing. So think about the cloud. The water evaporates from the sea all around the cruise ship, and it moves up, and the thought is that this water ought to spread uniformly over the sky, and yet somehow it doesn't quite. The water vapor actually coalesces into discrete clouds. Now, why is that? How come the humidity inside the cloud is 100% and right next to it it's practically 0? How come we don't know the answer to that? Maybe some of you do. Is it because we really don't understand water as well as we think we might? This stuff right here. Also, consider lightning and thunder. So you see a lightning flash that goes to the ground. Now, remember, all of this is just water, and all we have in the system is water and radiant energy that comes from the sun. So the question is, how is it that simply water and radiant energy somehow give rise to all of this energy, which is unleashed in a thunderclap and in a flash of lightning? How does that work? And traveling beyond the skies, consider common Jell-O. This is mostly water, right? This is protein and 95% water. And if you pick up a piece of Jell-O, how come the water doesn't dribble out? There's so much water inside. Well, if you look at what Jell-O might look like, a Jell-O is a network of protein, and gels are networks of either protein or polymer. And they're hollow inside. They have lots of big open spaces that are, in most cases, just filled with water. So how come this water doesn't just dribble out? The water molecule is a tiny fraction of one of those small strands. Another unknown, we see the water bugs walking on the surface of the water, and of course they keep up, as you know. And the same thing happens with a coin. Now the coin is heavier, by far, more dense than the water. And how come it floats? Well, some of you, of course, know the answer. Obviously, it's surface tension. And the reason we have surface tension is that the molecules on the surface are kind of hooked together, so you have 2 or 3 layers, perhaps, of water that are different from the rest. But how can a few molecular layers create such high tension? And how is it that when you dive from a high diving board, you run the risk of breaking your neck? So that's not quite clear. Now, from the lab, there are some more puzzling observations that we don't really know about. So take a beaker, as an ordinary beaker, and fill it with a suspension of microspheres in water. Microspheres are these tiny little spheres that are 1 micron or 2 microns in size. They look like a tiny little pea, and you put a lot of them into the water. They're suspended, and that's why the water looks cloudy. So you pour them into the beaker, and you wait, say, overnight, and next day come back, and what do you think you see? You see a hole in the middle. Now, if that's not counterintuitive, I don't know what is counterintuitive. Somehow the microspheres leave some point near the center, it doesn't need to be the center exactly, and migrate toward the periphery. Why do they do that? What's the reason? Now here's another observation. This looks pretty simple. You might set this up in any laboratory. There are 2 beakers sitting right next to one another, and they're filled with water. So put an electrode into one beaker and another electrode into the other beaker and put a high voltage between them. So what do you think happens? What happens is first there's a bridge that's created between the 2, and then if you pull one beaker away from the other, the bridge is maintained. It doesn't collapse. And you can extend this out for basically for an inch or so, and it still doesn't collapse. This is just water. There's nothing else between it. Water. How come? Suppose there's a real chemistry inside the water, and might we have a different kind of understanding? Maybe some fresh, unifying understanding of nature might actually result. And that's exactly our direction. That's where we're headed today. That's what I'd like to be discussing. So if we start with a simple water molecule, I think most of you know this, oxygen and 2 hydrogens. It's actually a dipole with positive charge on one side and negative side on the other, and we can represent it by a simple bean or something like this. So we have a dipole, and if you have a surface with a charge on the surface, then you expect that these dipoles would begin absorbing onto it. And if you have a lot of charges on here, you'd expect that these dipoles would absorb, and you get a few layers of these dipoles. And because they're wiggling, because of thermal motion, you expect that this array of dipoles will have a finite extent. And the current theory is that these dipoles may extend out 2 or 3 molecular layers, but not beyond that, because this kind of thermal motion then begins to destroy this lattice. Any book that you read will tell you that. So the water, it seems, is not very interesting. The water is just a couple of molecular layers that are ordered, and beyond that, all the water is essentially normal bulk water. So not very interesting. On the other hand, what I want to show you today is that this array doesn't end in 2 or 3 layers. It extends very, very far, and that will be the message today, and I'll be discussing why this is so important. We're not dealing with 2 or 3 layers, we're dealing with 2 or 3 million layers of water, and the water tends to be the dominant feature, this ordered water. So the initial experimental approach to figure out how far this array might extend was a very simple one, and perhaps a naive one. So you have a surface and you have some degree of ordering, and we know that if you throw some solutes into the water, that the solutes tend to be excluded from any crystalline-like region like this. For energetic reasons, they prefer to be in the region beyond, where the water molecules are freer, and they can be used to hydrate the particular solute. So the idea is to put some solutes in and see how the solutes distribute. And from the distribution, you just look at the region where there are no solutes, and you can figure out roughly how far this might extend. And that was a simple approach. And the guy who started in the lab with me is Jim Zhang, who I think is here. And Jim was a postdoc in the lab for quite a while, and he did many of the initial experiments. So the first experiment is really simple. We take a gel. In this case, it's a polyvinyl alcohol gel. And here's the boundary of the gel. And we took a suspension of microspheres. Microspheres, remember, are these tiny spheres. Put them in water and pour the suspension onto right next to the gel and see what happens. This is a 10 micrometer scale, so bear that in mind. And what happens is the following. So this is one of the first videos. It's, you might say, historical. These microspheres begin migrating from the surface of the gel. And they keep migrating and migrating. And this was stopped prematurely, but finally they stop around here. So there's a zone that extends maybe 50, 60, 70 micrometers. That's hundreds of thousands of water layers involved from the surface. We tried several other gels. Here is a different gel. This one is polyacrylic acid gel. And the gel runs from this boundary to this boundary. And this is just a reflection, so don't worry about it. And you can see that the exclusion zone on this side and this side, the microspheres are here, extends for 250 micrometers. That's a quarter of a millimeter. So you don't need a microscope to see that. You can see it with your naked eye. So this is the so-called exclusion zone, and we call it exclusion zone EZ, or easy water, as opposed to hard water that contains all the stuff. We call it that. And so the first thing is that there must be some trivial explanation for this, or some artifact, because this is completely unexpected. This is a region that's so large that you'd think that somebody would have found it earlier. In fact, we found, to our chagrin, that 35 years ago someone did find it earlier, but we hadn't known about it. So we spent a year searching for possible trivial explanations for this. And the ideas are, one is that, well, maybe the gel is shrinking. And as the gel is shrinking, the water is coming out. And that's what you're seeing, is the water that's coming out. Another idea is that the microspheres are interacting with one another and thereby pulling away from the surface. And another is that polymer may be diffusing out of the gel, and that region contains some stuff that somehow mysteriously creates that zone. It could be that polymer strands are protruding from the surface. You can't see them in the microscope because there are just a few, but enough to push the stuff away. And some kind of mysterious long-range repulsive effect. Well, I'm not going to take the time to go through every one of those because that will take too much time. It's published, and anybody who's interested could read about it. It seems to imply a very long-range ordering of water that is unexpected. And if this is true, then much of the water in the universe may be, rather than the bulk water that appears in the textbook, may be like a liquid crystal. And if so, then this may provide a fresh basis for understanding of water that possibly can answer some of the questions and resolve some of the anomalies that I've shown. So getting to the basis of this long-range exclusion, what I want to present to you is a series of questions. There are 5 questions that I want to answer in the rest of this talk. First, is this something general, or is it just highly specific to those few gels that I mentioned? Does it really arise from ordering of water, or is there some other explanation for this? Can water ordering explain some of the anomalies that I presented to you at the opening? And this sort of ordering needs energy. Where does the energy come from to give rise to this? And finally, what critical issues might these findings resolve? Why should we even care? So let's get to question number 1, the generality. And we're talking now about surfaces and solutes. Is this general in terms of the types of surface that give rise to this? And there are 2 types of surface that we might consider. There's hydrophobic, that is water-hating, and hydrophilic, water-loving. And some of you may be familiar with these. Hydrophobic surfaces are ones, if you drop some water on them, the water will bead up, just like water on wax. And hydrophilic surfaces, the water spreads out uniformly on the surface. And we found that hydrophobic surfaces do nothing like that. Only hydrophilic surfaces. And to give you an example of what we've looked at various hydrophilic gel surfaces, and you don't need to know the names of these, but they all exclude. They all show this exclusion phenomenon. We looked at biological specimens, and one example, since we've been dealing with muscle for a very long time, this is the surface of a mussel, and we expose the muscle to microspheres actually in an aqueous buffer. And you see that the exclusion is certainly not as complete as it is in the case of the gels, but there are many few microspheres nearer to the surface of the muscle than farther away. So it appears to be, that's just one example of quite a few biological samples that we've looked at. We looked at monolayers. Monolayer is a single molecular layer, and to the left of that is a gold surface, and the monolayer is laid on the gold surface and contains some charge groups. We've used various charge groups. And you can see that right next to the surface, there is a fairly decent sized exclusion zone, and the microspheres are here. And we've used polymers. The most convenient one is Nafion, which is a polymer that's been used a lot in fuel cells. And if you look at the 200 micron marker here, this is actually an arrowhead cut out of a sheet of Nafion. The sheet is very thin, and it lies in the plane of the screen. So we'll watch what happens with time. This is about 20 times real time. So you can see how the exclusion zone is opening up, and it continues. Again, it's cut off prematurely, but it continues to about 500 micrometers. That is half a millimeter or something like that, or 400 micrometers. It's macroscopic. So in terms of generality, we've looked at many hydrophilic surfaces, and they all show this kind of exclusion. So we think, in general, that hydrophobic or charged surfaces give rise to this exclusion as a generality. Now getting to solutes, which solutes are excluded? We've looked at polystyrene microspheres, silica microspheres, red blood cells, bacteria, colloidal gold, and ash, and dirt from outside of our building. Now, I'm not sure if the dirt outside Kane Hall is similar, but we've seen it. If we go to smaller solutes, one of the solutes that we've looked at is protein. Now, albumin is a typical protein that's explored by many people. This is a time series going from the top to the bottom. And you can see in the upper panel, you can see the Nafion because it fluoresces. And it's just right next to water. That's all you see. The second panel down, we added the protein, the albumin, with a fluorescent dye. And you can see it glows brightly. But you can also see on the right side that there's an exclusion zone that's growing, and it grows and grows. So the result is that protein seems to be excluded similarly to the microspheres. Even smaller solutes are shown here. So again, this is in the upper left, we have a piece of Nafion, and this is water. And in the second panel, at 1 second, we add sodium fluorescein, molecular weight 376 Daltons. And you can see that very quickly there's a zone that forms, it gets wider and wider. Now even smaller than that are various pH-sensitive dyes. It's a collection of molecules that are typically 100 or 200 Dalton's molecular weight. At the bottom, we have a piece of Nafion, and just above that is the exclusion zone, which contains no dye. The dye goes from here to here. So the dyes are excluded, but there's something else that's interesting that may have caught your eye. It appears like a kind of rainbow of colors, and the rainbow of colors means that there are differences. There's a gradient of pH. It means that in the region closest, there are lots of protons, fewer and fewer, and that will be very important in a few moments. But for now, the important observation is that the dye is excluded. So in terms of question one, the issue of generality, many hydrophobic surfaces generate exclusion zones, and many solutes are excluded. So it's a fairly general phenomenon. We move now to question two. Question two is this zone really physically different from bulk water? We use several methods to see whether that zone really is different. And I'm going to show you a few methods, if you bear with me. The first is nuclear magnetic resonance. Now what that does is it tests for molecular freedom. The molecules are perturbed by a magnetic field and they relax. And from the relaxation, you could tell if the molecules are constrained or free. And here is basically a map showing what happens. This is a gel next to water at the bottom. And look at the interface region corresponding roughly to the exclusion zone. Dark regions in this kind of image mean that the molecules can't easily rotate. So we have a region that's roughly the size of the exclusion zone that's different from the rest of the water. So the conclusion is that the exclusion zone water molecules are more constrained than other water molecules farther away. We next looked at infrared radiation. Now that's the radiation is what you pick up when you use an infrared camera. So even if the lights are off, you use the camera and you can get an image. Now the image, the intensity at a given point is a function of the temperature and of the emissivity, a property of the material. So what we see here is a piece of naphthalene at the top, bounded by water, no microsphere, just water. And if you look at the water region, you can see that the top region of the water is dark and the bottom region is light. So it looks like there's some kind of boundary between the two. Now, as I mentioned to you, the water there could be dark because it's colder than the water just below. This is an image that was taken over many minutes, averaged over many minutes, and there's no reason to think that there should be such a sharp, large temperature gradient that could be sustained for so long, because temperatures like to become uniform. The other interpretation is that the structure in the region that's darker has a lower emissivity. That is, it's more stable, and therefore it doesn't radiate as much as the rest of the water. And that's the most likely interpretation of that. So it looks as though the exclusion zone is more stable than the water beyond. Another one is to measure the electrical potential, because electrical gradients imply that you can have separation of charge. Now, that's not expected in water, because water should be neutral. So we made measurements that you see here. And what we did is we had a gel on the left side and water on the right side. The right side labeled outside is outside the gel. And we used a pair of electrodes, actually microelectrodes. One of them is remote, sitting out here somewhere beyond, and another one is placed at different locations, different distances from the surface of the gel. Now, if we look at the one labeled PAA, that means the gel here is polyacrylic acid, which I showed you earlier. And if you start making the measurements, you can see that the potential difference between this point here and a point farther away is 0, which is what you expect. But as you get progressively closer to the surface, you begin to pick up negative potential. That negative potential corresponds roughly to the size of the exclusion zone. If you look at the one that's labeled naphthalene, we do exactly the same experiment, but instead of the gel, we put a slab of naphthalene at the boundary, and we make the same measurement. And here, you can see that the electrical potential begins to get negative farther away from the surface. And sure enough, correspondingly, the exclusion zone for naphthalene surfaces is bigger. So basically, wherever you have an exclusion zone, you have a negative potential. And what the negative potential means is that you've got negative charge. So we have a situation that looks something like this. But there's something that seems wrong here, because we have water. And how is it possible that water contains negative charge? That doesn't seem to square well with our intuition. So there are two possibilities. One possibility is that this region of water somehow gains electrons or gains charge that way, or it could lose protons. And we thought the latter was more likely, and so we investigated, and sure enough, when we made pH measurements of the region out here, we found huge concentrations of protons. Remember that slide I showed you? I'll show it again in a moment. So now it's turned at right angles from before, and at the left side, the red zone shows the naphthalene, and the zone here is the exclusion zone. And remember from the previous slide where we measured the electrical potentials, this region is negatively charged, and it's negatively charged because we have a huge concentration of protons, positively charged protons out here. So basically, what we have is an exclusion zone right here that's negatively charged, and the zone beyond, the zone of water, is positively charged. It's a battery. If this is true, then we'd expect that if we put an electrode in the negative region and another electrode in this positive region, we ought to get current flow between the two. And sure enough, that's exactly what we get. We measure current, as a function of time, and we get a curve that looks like this. So there is demonstrably current flow between the negative zone and the positive zone. And this confirms that, indeed, the charges are separated. So the electrical potential measurements show that this exclusion zone has negative charge, and ordinary water doesn't have this. Now, the next one is the light absorption spectrum, and I'm not going to go infinitely with these, but light absorption spectrum. And this typically distinguishes electronic states. And so to do these experiments, we use the setup that looks as follows. We start with a slit, and the slit is approximately 100 micrometers wide, so the light goes through the slit. It creates a narrow window of light that goes through a second slit and then to a spectrophotometer. And the guts of the experiment are shown here in this cuvette. So we have a slab of naphion on one side, and we have water on the other side. And what we can do is we can shift the position of this cuvette along this way, so we can interrogate regions very close to the naphion, where we have the exclusion zone, and regions farther away. And that's the essence of the experiment. So the results are shown here. This is wavelength on the abscissa, and the amount that's absorbed on the ordinate. And you can see that at 400 microns from the surface, and the exclusion zone is 400 or 500 microns, there's almost no absorption. As you get closer, you pick up a huge peak of absorption, almost enough to saturate the machine. It's at 270 nanometers. And so what we see is that the exclusion zone has this very strong characteristic absorption, but bulk water has nothing. So from that, we conclude that there is definitely something different about the exclusion zone. Next, we look at viscosity, and we use a very simple method, falling ball viscometry. So we're looking at the velocity with which this ball falls. And of course, our interest lies in the zone just above the naphion, because that's the exclusion zone. And the question is, do the balls slow down when they get there, indicating a higher viscosity? So this is a movie taken of some of these falling balls. And starting at the top, they fall with a reasonable speed, and then in the middle, they fall with roughly the same speed. And as you get close to the surface, this is the surface of naphion, you can see that they slow down, almost stop, and they go through very, very slowly. And if you plot this is height on the ordinate, you can see that we have the falling ball, and as the ball goes down, it slows down. And because it slows down effectively, it means the viscosity becomes much higher. And this is a control with no naphion. This is a surface that has no exclusion, and you can see that there's virtually no effect. So the exclusion zone then is more viscous than ordinary water. And finally, we've begun using polarizing microscopy. The first experiments were done by Gerhard Artmann in Aachen, Germany, and he did this in one morning while I was there to demonstrate it. Here's an agarose gel next to water on the right side, and you can see that at the edge there's a region that corresponds again roughly to the exclusion zone, where the molecules are aligned as a result of this bright region. We also have begun experiments together with Werner Kaminsky in chemistry, and you can see that same image of an arrowhead shape of a piece of naphion sitting in water. And the water is blue, and the colors indicate, wherever you see a color, you see that there's some alignment of molecules. So the aligned molecules at the edges correspond very nicely to the exclusion zone that you saw, both in size and in distribution. So where we've been answering this question is that we've seen first that the exclusion zone water molecules are constrained compared to water beyond, which is not constrained. The exclusion zone molecules are stable compared to the bulk water, which is less stable. The exclusion zone has a negative charge compared to ordinary bulk water, which doesn't. The exclusion zone absorbs at 270 nanometers compared to bulk water, which doesn't. And the exclusion zone is more viscous than ordinary water. And the molecules inside appear, based on our preliminary evidence, to be aligned. So clearly, the exclusion zone water is different from ordinary water. And if you look at the top two and the bottom one, then we can learn a little bit more about this water. The molecules are constrained The molecules are more stable, and the molecules appear to be aligned. What that means is we have a liquid crystal. We have a situation where molecules are very well aligned with one another. So far, where we are is that we have a region that excludes solutes, has negative charge, is liquid crystalline, and extend very, very far. You might think that this could be thought of as maybe as a fourth phase of water. We all learned in our chemistry books that water has three phases, right? It's got ice, and then you have a liquid, and then you have a gas. But this appears to be somewhere in between. And it was suggested, not by me, but by Sir Thomas Hardy in 1912, almost 100 years ago, that there's a fourth phase, and this is the liquid crystalline phase. It's surprising how much work was done over the years, 100 years ago, on this subject. In fact, we recently dug up something that you can't read very well. It's called the depth of the surface zone of a liquid. And if you could read in the upper right, it says 1949. This paper, published in 1949, summarized all the evidence for various liquids near surfaces. And there are more than 100 references of studies done before 1949 that demonstrate that these liquids are organized, and they're organized for regions on the order of hundreds of microns from the surface. What happened is that after around 1950, by around 1950, this was well known. For example, Albert St. Georgi, who won the Nobel Prize for discovering vitamin C and made many other contributions, in one of his several books, he said, life is water dancing to the tune of macromolecules. So at that time, it was really well known that water was critically important. So what happened? Well, what happened is that there were a couple of debacles, you might say. One of those involved something called polywater that was found originally by the Russians and found to be an artifact, almost a joke. And then 20 years after that, there was another event. Now, this one was called water memory. And again, this turned out to be another debacle, and someone lost his career by suggesting that water molecules might have memory. And the advice I remember getting early in my career, when I didn't know anything about water except that it was good to drink, is you can do research in any subject, but stay away from water, because it's really dangerous. And I think that's what happened for a period of 50 years. And that's why some of the information from the first half of the last century is completely lost. So the answer to question number 2 is that is the exclusion zone physically distinct from the bulk, is that yes, indeed, and it appears to be liquid crystalline. Okay, question number 3, can crystalline water explain some of the counterintuitive observations that I showed you at the beginning? What kind of behavior do we expect from liquid crystal? Well, we expect, you know what crystals are like, and you know, for example, crystals grow. And so here's an interesting slide taken from our laboratory. This is a piece, at the bottom is a piece of Naphion, and pardon these little bumps here. When you put Naphion down, stuck to the surface, when it hydrates, it expands. And this is just a simple result of expansion. It has no other importance. But notice that the exclusion zone down here doesn't simply confine itself to this region parallel to the surface. It begins to grow. And you can see that it grows here as well. In various positions, it grows for very long distances. You'll notice also another feature is that it's surrounded by red. Now remember, red, these dyes, indicates positive charge, indicates protons. So it's really interesting that as a crystal, you expect growth of the exclusion zone, and it really does grow. And it's surrounded by protons in just the same way that this region here is surrounded by protons. Now, it's not just, we can see this not just with these dyes, but also with microspheres. So I know you can't see this too well, but I hope you can see it. This is a giant chamber that's 1 meter long. And here is one end of a cylindrical chamber. And there's a piece of Naphion that sits at the left side. And perhaps you can see there's a regular exclusion zone right next to the Naphion. But it keeps growing, as you can see here, and it grows, and it'll grow all the way sometimes to the end of a 1 meter long chamber. You could see it again here. I know these images are difficult, but they were difficult to photograph. This is another big chamber, and again, the exclusion zone grows, and sometimes it even branches. So this is exactly the kind of observation that you'd expect from a crystal, because crystals tend to grow. Crystalline components also stick together. Elements of the crystal stick in order to build the crystal. And if we go back to our friend, the Jello matrix, you can now understand why the water doesn't dribble out, because the crevices are not filled with ordinary bulk water, they're filled with liquid crystal. The crystal sticks to the surface of the protein and also sticks to one another layer, and so there's no dribbling. Crystalline water is actually, this crystalline water is more or less gel-like, so you can understand in these cases where you have mostly or almost all water, that the gel consistency that you feel, even in Jello, is conferred probably by the water and not by the protein in the gel. Now, we found that this kind of crystalline water also grows at the interface between air and water. So you have something like this, and the air-water interface, you'll find some of this material. And here's an example of such. This is a chamber built of two parallel glass sheets, and the sheets are parallel to the surface of the screen, and they're pretty close together. So we fill this 2/3 of the way with microspheres and water. And what happens after a few minutes is shown here. So at the top is the air, that's the dark region. Then there's a meniscus, that white line that runs across. And at the very bottom, here, cloudy, are the water plus microspheres. And what happens over a period of time, it takes about 20 minutes or so, is that an exclusion zone, a clear zone, develops at the top, which is very much like the exclusion zone that I've showed you. It has no microspheres. And this is not because of settling of microspheres. That occurs over a much longer period. They're heavier, they sink to the bottom. But this is stable over a period of hours. And so the clear zone is very similar to the exclusion zone, and it actually constitutes a thick gel-like band. Now imagine now at the surface, we don't have 1 or 2 molecular layers, but we have a thick band that might be a millimeter thick. It might have 3 million molecules or something like that, and it has a gel-like character. Now watch what happens in this movie as we take a glass rod and we come to the surface. So here's the surface at the top, and here's the clear zone. What we're going to do is touch the surface and then move it along and see what happens. And I'm suggesting to you that this gel-like band, you'll be able to see the existence of it. I hope, if it shows. Oh, here it comes down. Now watch, as you move along from side to side, you can see that the microsphere gel boundary, that the bottom mound moves along with the top mound, indicating that that band is a contiguous band of fluid, a contiguous gel-like band. And so that explains why things that are heavier won't sink in water, because there are many structural layers, not just 2 or 3 structural layers, but 2 or 3 million structural layers that create the very high surface tension. Okay, now crystals also, as those of you who have diamonds know, can be pretty stiff. And so we go back to this bridge that we see that expands without breaking. Unlike the Tacoma Narrows Bridge, this water bridge is very stiff, and we can understand that if the water is composed of a liquid crystal, crystals can be stiff, and that is perhaps what gives rise to this stiff link that you see here. And finally, the reason that the protons on the right side, the free protons, don't enter into this exclusion zone, which is on the left side with the negative charges shown, is that it's a liquid crystal. If it were not a liquid crystal, imagine what would happen. You've got negative charges on the left, positive charges on the right. The two would come together so quickly like a flash of lightning and dissipate. But that doesn't happen, and the reason is because this is a liquid crystal. So the battery charge remains separated as a result of the crystalline nature. So the answer to question number 3 is, yeah, crystalline water does explain some of the anomalies in a fairly simple way. It explains also why the water battery charges remain separated as they do. Question 4 is, what charges this water battery? Again, you can't get something for nothing, right? And so in order to build the structure, to separate the charge, it's like your cell phone battery. You know, you have to plug it in, otherwise it's dead. So the question is, what's responsible for charging and recharging this battery? And it turns out after several years we found what we think is the answer, and it's incident radiant energy, for example, from the sun. This was somewhat of a surprise. What you see here is a piece of naphion. Here everything is illuminated with green, simply to restrict the amount of light, because we want very little light, because we're testing the effects of added light. If you look at the microspheres, they're shown in the distant region, and the exclusion zone is shown here, devoid of microspheres, and the light is turned on, and it's a point source of light. So the light is very intense here, and it's less intense at these places. And I think you can see what happens to the exclusion zone. The place where it's lighted, the exclusion zone grows greatly, almost like that liquid crystalline icicles that grow. Another experiment, when we used a particular wavelength in the near-infrared illumination, this is a rather startling result. Here's the control on the left, and the exclusion zone is shown here, of sort of standard size. And then we expose the specimen to infrared radiation, in this case 3.1 microns, but that's not so important for this. And we do it for 5 minutes. And what happens is that this exclusion zone grows by 3.5 times in 5 minutes. Now you might think infrared light, of course it heats. When you're under an infrared lamp, everything gets warm. So you might think that this is somehow due to heating. And so we measured the temperature in various regions over the chamber, especially in the region near the exclusion zone, and the maximum temperature increase we saw was 1.5 degrees. So this is not due to heating. It's due to some direct effect of the photons that come on the exclusion zone. Of course, we're interested to see how different wavelengths behave in terms of the exclusion zone size, and pardon the apparent complexity of the graph, but we're plotting on the abscissa wavelength, and this is the visible region, roughly from 400 to 800 nanometers, and the UV region is to the left, and the infrared or near-infrared region is to the right. And so we test every wavelength, or the ones that we could test. For example, if you took a green light and exposed the specimen to green light, you'd find that the exclusion zone went from 1.0, the control value, to say 1.6 or so, a 60% increase over 5 minutes, and so on. Over in the near-infrared zone, you can see again that different wavelengths have different effects, and the most prominent effect is at 3 microns, the so-called OH stretch region. But notice I put here that the light intensity that we had at our disposal was weaker by 1,000 times than the light we had here. So if you had a similar intensity, then the curve might look similar to this one, but it would be shifted way up. So if you look over the entire spectrum, this would be a continuous curve. The highest point would again be at 3 microns or so near infrared, to which the specimen is exquisitely sensitive. So the answer to question 4 about the energy, where does the energy come from, is that this exclusion zone buildup is powered by photonic energy. And this photonic energy, whether it's from the sun or from artificial light or from infrared that's coming in all the time, orders water, and it charges the water battery. So a possible energy flow in the universe looks something like this. Now this is the conventional one. The conventional one is that we have the sun hits the water, there's lots of water, hits the water heats up, and so energy from the sun basically heats up the water. We all know that. There's nothing unique or interesting about it. What I've shown you in the previous group of slides is that there may be another path. The other path is that the sun hits the water and it imparts a different kind of energy, an energy for building order and separating charge. And from the experiments I showed you, this is the dominant effect, not the trivial effect. So this is a kind of new, fresh paradigm for how the energy in the universe is distributed. Now, okay, so why is all of this stuff important? That's the 5th and final question. I think that this sort of, these observations that I showed you are foundational for any and all science involving water and light. that goes from physics to chemistry and biology. But not only that, and we've seen an example in the previous slide about the new paradigm for energy, but also foundational for engineering of genuinely new and practical devices, because based on this new principle, it ought to be possible to engineer some devices that people had never really thought about. So what I'd like to do in the first one is to give you one example, a single theme, interaction between water, particles, and light, to see how this might play out in physics, chemistry, and biology. And some of the biology is shown in the book that was just shown has been detailed in this book. So I'm not going to focus too much on the biology. But think about what happens. Suppose you have a charged particle or a molecule sitting in the middle. The conventional view is that there may be one or two water layers around it, and that's about it. What I've demonstrated to you is that's not correct. There's a lot of water around it, and this water has negative charge. And because of this negatively charged water, there are protons that are generated all around this construct. So it means the situation is very different, and in simple chemistry in the laboratory, we're dealing with not the structure that the textbook says, but a structure that's more interesting, that has a lot more, you might say, capability. Now, just to give you an example of how this might work, consider two particles that look like this. So you have two particles, they've got negative charge, extensive negative charge around them, and lots of protons all over the water throughout. Now, if you're a particle, like maybe the one on the right, and you look around, you're negatively charged, and the thing that you crave most is positive charge, right? And so you look around and you see positive charge in this direction, in this direction, in this direction, and in this direction, and you're going to move where the positive charge is most concentrated. Now, which direction is that? Well, you can pretty much predict that the positive charge distribution is pretty much the same here. But when you go into this region, between the two, then the positive charges come both from this one and from this one, so they're more highly concentrated. What that means is that the particles will tend to come together. Even if they're far apart, they'll tend to come together as a result of this. And this coming together is actually really well known, at least to some groups of people. And it was labeled by the famous physicist Richard Feynman as like likes like. So basically you put some particles that have the same charge into a container of water, and you expect they'll repel each other, but they attract each other. Like likes like. So the particles will come together, and you reach an equilibrium in a situation that you might guess. It's when the attractive force between this entity and protons is balanced against the repulsive force between these two negatively charged entities. Then you have stability. Now I showed you two particles, but in fact if there are a lot of particles, all the particles will come together in some stable point. And the person who's done the most to show this is a colleague, Norio Issa, at Kyoto University, and one of his results is shown here. So you take a beaker and you put water and a few microspheres fairly widely dispersed in water, and after that you just wait. And if you wait and look with a microscope, you can see that these microspheres have all come together to form what looks like a crystal. And it looks like they don't touch each other, they're slightly separated, as you can see, and this is called a colloid crystal, and it's very well known. So like likes like, a very fundamental principle of nature. So if we look back up at our cloud that we started with and ask the question, how come this water that's rising uniformly condenses into a cloud? I think we have some understanding. It's because like likes like. And if we look at the beaker with the hole in it, where the microspheres aren't, the reason that a hole is created is because light is coming in from all sides. Light, infrared light, visible light, what have you. And as a result of this infrared light, the microspheres get drawn toward the periphery, leaving a hole somewhere at the center or near the center. It depends on the uniformity of the light that comes in. In fact, once this has been formed, if you take a light, not even a bright light, and you put it on the right side, then the microspheres move toward the right side and the hole moves toward the left side. So it's light that pulls the microspheres toward the periphery. Now, finally, another example of like is perhaps one of the most fundamental questions of science, the origin of life. What's step one in the origin of life? There may be different views on this. Step one, in step one, we have dispersed molecules that somehow coalesce into some entity that looks sort of a bit like a gel. So we can imagine the shallows, and we have a bunch of simple molecules that are spread out. And to that, we add sunlight. And if we add sunlight, we know from the previous slides what happens. What happens is the molecules coalesce. They tend to come together, forming some sort of a cluster. And this kind of cluster, this aggregate, keeps growing, just like a cell keeps growing. It has negative charge, like the cell has negative charge. It has potential energy, like the cell has potential energy. It has the capacity to divide, either by agitation or by putting a solution in one spot with a different pH, etc. So step one may be simple light-induced aggregation. And all you need for this, remember, you need water, you need molecules, and you need the sun's energy. That's all. And so if that's all you need, then the question arises, is life being created continually? It might be that life around us is being created this very moment. So in terms of question 5, why should we be interested in all this stuff? I've given you some demonstrations of how scientifically how these things might play out. And I think one of the aspects of this is I didn't divide physics, chemistry, and biology because what I just showed you is a unifying theme for all of physics, chemistry, and biology. Finally, I suggested to you that these new kinds of principles ought to be pertinent for engineering of genuinely new practical devices. And that's what I'd like to end with, was a couple of devices. Now, one of them is purifying contaminated water, something that's useful. You remember that the hydrophilic surfaces like Naphthalene give rise to an exclusion zone. Well, how could you forget? Okay, the exclusion zone, the large exclusion zone that you see in dark to the right, and the microspheres farther to the right. And we found, interestingly, that this happens not only in a static situation, but if you have flow in the direction that I show, this exclusion zone persists. And so we took advantage of this finding. And at the left, you can see it's a tube made of Naphthalene, and the flow is going to the right, and we have microspheres that are flowing in the system. It could be anything, any of the solutes, but here we see microspheres. And as it flows toward the right, the exclusion zone begins to build up, and you have a very big exclusion zone right here, even though these are flowing. Still, the exclusion zone is maintained. So what you do then is you build an extractor of some sort which segregates the core region from the annular region here. And so the concentrated stuff goes out this way, and the stuff that is purer is collected here, and the dilute, the purified water. And this is one representative result showing that the microspheres are indeed concentrated on the right and less concentrated on the left. And this was an early result. We've since demonstrated separation on the order of 1 to 200, which I think is pretty good on one pass. And we found also that bacteria are quite separable. So the idea is that perhaps you can take some water that contains bacteria, just put it through this filter. It has no physical filter. It just filters based on the principle that I've been describing to you and collect the pure water. And so we're scaling this up for practicality. And I might just make one point, is that the exclusion zone water is not, remember, it's water that has some perhaps crystalline-like structure. And the question is, well, can you drink this stuff? Well, it turns out that a lot of people are selling it. And these people are claiming that this has some health benefits. And if you think about it, if your cells are filled with this kind of water, it may be okay to drink some more of it. I'm not so sure, but it's quite promising in terms of possible health benefits, not just to satisfy your thirst. And finally, the idea of getting real power, electrical power, from light and water. So remember the situation on the left side, we have negative charge. On the right side, we have positive charge. And if you put 2 electrodes in there, you ought to be able to power a light bulb. And we've been able to do that. We've been able to get current and voltage, power from these 2 regions. And this is a plot here of voltage as a function of time. And on the left side, the signal is beginning to wane after some time. It's getting weak. Turn on the infrared light, and it goes way up. And it actually lasts for some time. It's what we expect from the effects of light or infrared radiation, which is coming from everywhere. And so we get a real boost. So it appears, again, that this kind of power that's coming out, electrical power, is boosted by light. And so the idea is that all you need basically is water, a surface, and light to get electrical power. Water plus light gives you charge separation in the water, which gives you energy that you can harvest. Now, you think for a moment, there's something else out there that does the same thing. It's plants. Not only plants, but also some kinds of bacteria, cyanobacteria. They take light, and in water there's a separation of charge. That's what we have here. The process at the left is known as photosynthesis. The process at the right we call artificial photosynthesis, but I suspect there's no real difference between what we've demonstrated in water next to a hydrophilic surface, no real difference from what actually goes on in plants and bacteria. I think we've actually found the basis for photosynthesis in doing this, and it lies right in the water and with the energy that comes in from light, especially in our case infrared. So we're getting electrical power basically from photosynthesis, and right now the amount of power is not so great, but we're working energetically to try to see if we can scale it up. And of course the question arises, and we don't know the answer, but you know, who knows if that might be the case. After all, photosynthesis is a very efficient kind of process. So I've given you two examples of some new, genuinely new practical devices that might arise based on the new principles that I've been describing. Now the reception's coming, and I think there's going to be food, but we need to remember that that there's also water, and that the water is good to drink, and that water is also sometimes inspirational to watch. And also, finally, I must say that in terms of all of the studies that I've demonstrated, which is really a small fraction of what we've done, it's all been done by the crew of people in the lab, and this is a marvelous crew of people ranging from some staff members and postdocs and graduate students and a host of undergraduates who are very excited about what they're doing. And all of these people come together and have done the experiments that I've told you about. And I must say, these people are really immersed in water. And even more immersed is the boss, who maybe is down under, is maybe all wet. Anyway, thank you very much. Okay.